In this video, we show why the zero conditional mean assumption is a necessary condition for the OLS estimator for our slope parameter beta1 hat to be an unbiased estimator of the true parameter beta1. We start by reminding ourselves of the definition for an unbiased estimator. So if the expected value of beta1 hat conditioning on our xi's is equal to the true parameter beta1, then we say that the OLS estimator is unbiased. Okay, so we start by writing out the OLS estimator for beta1 hat, and I'm writing it in this particular way as a function of yi, as we'll see shortly. But before we continue, let's just stop for a moment and think about our third Gauss-Markov assumption, which requires that we have variation in our explanatory variable x. If we didn't have a variation in x, then all of the xi values would be the same as x bar, and this denominator term would be equal to 0. Okay, so returning to our OLS estimator beta1 hat, we wrote it in this particular way with yi, so we could substitute in from the actual model. So we can substitute in for yi is equal to beta0 plus beta1 xi plus ui. For the denominator, we substitute in SSTx, which is the total sum of squares for our explanatory variable x, and we define this as the sum of the xi minus the x bars all squared. Next, we simply multiply out the brackets in the numerator, and remember that beta0 and beta1 are constants, so they can come outside of the summation terms. We can show that the first term in this numerator actually equals 0 simply by expanding out the summation term as follows. For the second term in the numerator, we can use useful properties of the summation notation to show that this xi minus x bar times xi is actually equal to the total sum of squares of the explanatory variable. So it's the same as SSTx. So all of this term here for the beta1 can cancel down to equal to 1. So we now have our expression for beta1 hat in terms of beta1, which is the true parameter, our xi's and our ui's. Okay, to demonstrate unbiasedness, we want to take the expectation conditioning on our x's of both sides. So we take the expectation of the left-hand side and the expectation of this whole term on the right-hand side. Next, we expand out the expectation operator. Remember, the expectation of a constant is a constant, so the expected value of beta1 is just beta1, and in this term here the SSTx is also considered as a constant, so that can come outside of the expectation operator. And finally, we can take the sum of the xi minus x bar outside of the expectation operator, because when we condition on x, any function of x, the expectation of that can also be considered as a constant. So now we can appeal to the zero conditional mean assumption and show that this expected value of ui conditioning on our xi is equal to 0, and therefore the whole of this second term is equal to 0, which leaves us with the result that we want, that the expectation of beta1 hat conditioning on x is equal to just beta1.